applications of the derivative. I think normally when you see the word applications in math, you get a little scared because you're like, oh, here we go with the word problems. And while that's true here, that it is word problems, derivative word problems are nice. You're going to find out derivative word problems are nice for a while here. It's going to be pretty straightforward what has to happen. You're going to be shocked how easy this is. This says applications of the derivative. I'm already unhappy with this situation. Let me just move this around a little bit. And fit that to width. There, that's better. Now I'm happy. Applications of the derivative. In many situations, it's very straightforward to know when it's time to do the derivative. We've done a little bit of derivatives where we're sort of good at them now. We sort of know how to take derivatives. But the question is, when do I do it? That's what I'm teaching today. When do I take the derivative? Let's read this question, which is totally rephrased from your note because it was phrased awfully in your note. So if you could fix it with my new phrasing. Here it is. A sphere is growing. We'll get to word problems thinking about why the sphere is growing. For now, you can picture one of two situations. Maybe somebody's blowing up a balloon, sort of sphere-like, and so the sphere is getting bigger and bigger. Or maybe a better example's, I don't know if you've ever seen anyone do this. Hockey players do this with tape sometimes. Every game, they take the tape off their shin pads and they wrap it around a sphere. And as the season goes on, it's unbelievable how big these spheres can get. Have you ever seen a hockey tape sphere? Yeah. My grandma used to do it with tinfoil. Every time she used tinfoil, she'd wrap it around, and then she had this giant tinfoil ball in her kitchen. Okay? So you don't have to have seen it before to imagine that every time you add a little bit onto the outside of a sphere, a little bit of tinfoil, it would get a little bit bigger. You wouldn't even notice it until I only saw it like Thanksgiving and Christmas. So I'd show up the next Thanksgiving and go, whoa, I couldn't believe how much her tinfoil ball was growing. And when it got a certain size, she took it outside and got rid of it and then started a new one. It was just this adventure she did. That's why the sphere might be growing. And we'll get to the specifics of the word problems. For today, it's just a sphere is growing. Find the instantaneous rate of change. Well, there, done. Lesson over in that phrase. Find the instantaneous rate of change. I'm going to highlight that right now and say instantaneous rate of change. As soon as you see that, you should immediately think derivative. Let's rewind a little bit. When you first saw instantaneous rate of change, it was 2 to 2.1, 2 to 2.01, 2 to 2.001. That was instantaneous rate of change to you. Last chapter it was limit as h approaches 0 and all the h's. That was instantaneous rate of change. And that all led to the derivative. So from here on in, when we see that, we're going to think derivative. That's the part of the question that tells me I'm doing the derivative now. And it says, find the instantaneous rate of change of volume. So apparently I'm going to go V equals. And then right after that, I'm going to do V prime. There's the plan. Oh, there's good teaching right there. Not difficult teaching, good teaching. This is what you need to know today. I've only read this far in the question, and I know what I'm going to do. I'm going to write down the volume equation for a sphere. Do I know the volume equation for a sphere? Do I have to memorize the volume equation? Hold on. Put all those questions up on the shelf. I'm going to get the volume equation for a sphere, and then I'm going to take its derivative. Then there's a new phrase, with respect to radius. And that phrase might scare you just a little bit. Like, what are you talking about with respect to radius? And I'll rephrase that for now. The phrase means, and the independent variable will be r. Maybe that's not surprising, that the independent variable will be r. But it won't be obvious moving forward as we go into other chapters. So this with respect to thing, this is the first time I've put that on a question, but you'll see that more and more, with respect to radius. And I'll show you what I mean by it when I do it in the question. But there's trouble coming here. This phrase is going to cause us some trouble. Well, after all that, does anyone remember the volume equation for sphere? And the last time you saw it might have been with me in grade 9. That's how little we do the volume equation of a sphere in high school. We do it sort of one day in grade 9. We do a bunch of homework with it, and then we sort of forget about it. But today it's going to come back, and maybe just the way I'm going to teach it, maybe you'll never forget it again. Oh, I gave some people enough time. K squared, what is it? Pi r cubed. There's a little hint in the formula. It's a volume, so it's cubed. So there's a little hint there about what formula it must be. So it's 4/3 pi r cubed. And before test time, we'll make sure you know which formulas you're supposed to remember and which ones you're not supposed to remember. So let's not put that on the panic table just yet. Let's just leave that and say, okay, apparently I might have to know some of these, but we'll worry about that when the time comes. So then v prime. Now this equation doesn't have x's in it. Virtually everything we did over the last couple of days was x's or maybe t's. So on those days, without really saying it, we were taking the derivative with respect to x or with respect to t. This time it's with respect to r, and that actually should make us happy. We're like, oh, take the derivative, but use r as your variable. That's what with respect to r is saying. Go ahead, use r as your variable, and that's what makes sense here, is to use r. Now I'm going to go over here for just a second and do a derivative, just to make something clear. Because the way I taught it, I might have confused the issue a little bit. I'm going to talk about finding the derivative of y equals 2x. Don't get scared. I think you probably know what the derivative is, but we've got to talk about it. What is the derivative of 2x? 2. What goes through your brain when you see that, though? Slow it down and really think about it and go, how do I know it's 2? What happens to me, what happens to my brain that I know that y prime equals 2? Yeah. So what exponent's up here? 1. So when I bring that down, I multiply it by 2, and then I reduce the exponent on x down to 0, and it becomes 1. Or, well, yeah, 0. The exponent becomes 0. But what I really get is 2 times 1. Okay? So the coefficient out front of a function just stays out front. It's just a multiplier. It's a common factor out there in the limit, actually. It's just sitting out front of the whole thing. So coefficients, I don't have to do much work with. I can put my finger over top of it if you want and go, find the derivative of x, which is 1, and then multiply by 2. In fact, I saw a couple people nodding there. That's maybe how they think about it. Derivative of x is 1, and then I've just got that 2 multiplier out front. Now, the way we've taught things, though, you may now look at that and go, oh, but that's really a product, isn't it? Shouldn't we have been using product rule? And the answer is maybe. If you did accidentally because you were doing your product rule homework, and then this came up, and you went, okay, product rule, here we go. Derivative of the first, the derivative of 2 is 0, times the second, plus derivative of the second, times the first. And so you get 2 anyways. Math isn't broken. It's okay. Product rule can handle this, but it might be laughing at you while you do it. Product rule might be going, what are you doing? Okay, I'll do it if you want, but you're going to get 0 over here. So you may as well just do this part. You may as well just go derivative of the second times the first, which is what we did over here. Really, we just did derivative of the second times the first, okay? Subtle point, but now comes up to haunt us here. 4/3 pi r cubed. If I want to take the derivative of this, what I really should do is just cover up the 4/3 pi. That's just a coefficient. It might look like a variable because it's a symbol, but pi is just a number. This is 4/3 pi, so this is like, well, 3.14 divided by 3 is about 1. It's about 4. The number out here is about 4, around that number. So when I go to take this derivative, what I'm really doing is saying, okay, leave the 4/3 pi out there, out front, then take the derivative of this part here, the r cubed, which is 3r squared. And when you're first learning them, you may have to do that. You may have to just go, I'll put the coefficient out front, I'm not going to worry about that, and then take the derivative of the variable part. So, is there any simplification to be had here? Do you see it? Can you see it? The 3's just go. So those 3's go, and this simplifies down to v prime equals 4 pi r squared. A couple of you knew the volume formula. What's that? 4 pi r squared. Georgia, do you remember what it is? The area of the circle is pi r squared. Their circumference is 2 pi r. That's surface area of a sphere. Just let that soak in for a second. Let's go back to Grandma's tinfoil example. How much is the volume of her sphere changing by the surface area? Exactly how much tinfoil she puts on the outside is how much the volume is changing. Whoa, those formulas are connected, and they're connected by the derivative. And when I taught it in grade 9, you're like, why is it 4/3 pi r cubed? I was like, oh, I really want to tell you. I really do want to tell you. But I got to do 2 to 2.1, 2 to 2.1. I got to do h's, I got to do limits. All to get down to, you bring down the 3 and reduce the power by 1. That's what was going on there. Whew, it's good stuff. On a Tuesday. Is it Tuesday? Sure it is. That's not the end though. And I did it with just symbols over there, but what I really should have done was I'm going to write it really small there. I really should have wrote V at radius r. These all should have been function notations, right? They don't have to be. And this was V prime at r. And this was V prime at r. That's what I really should have wrote there. But I didn't want to confuse the issue. But now that I have that, what they want is V prime at 3. They want to know how much is the volume changing when the radius is actually 3. So I can sub in the 3, 4 pi times 3 squared, and I get 36 pi. I'll get that as a decimal because sometimes the 36 pi is the confusing part for people, and I don't want that to be really confusing, even though 36 pi is awesome. You don't have to write, how many decimal places do I have to round off to? No, there's no discussion like that. 36 pi is 36 pi, it's perfect. But just to make sure it's clear what I'm getting at here, let's find out what 36 pi is as a decimal. I get 113.1, and the unit here is amazing. It's an amazing unit. It's how much is the volume changing with respect to radius. So it's centimeters cubed per centimeter. So for every centimeter you add on to the radius, you get 113 centimeters cubed of volume. Oh, that's weird. That is weird, weird stuff, except it's perfect. If you're looking at that and going centimeters cubed per centimeter, isn't that centimeters squared when you reduce it? I'm like, yeah, because it's a surface area we're adding onto the outside. Another great question that I could just stop there and go, you know what? Go sit under a tree for the rest of the afternoon and just stare at what's happened there and notice how much stuff has clicked together in one little geometry problem. There's a great area one in your homework. Spend some time on it, looking at it, going, it's not particularly difficult, it's just, what just happened here? It's good stuff. Any questions about number 1? Georgia. Should I write them for the decimal one too? Is that what you asked? Should I have it there as well? Yeah, for sure. I just did it with exact and then also with decimal because I didn't want the exact to be confusing. I didn't want people to stare at the 36 pi and go, what's going on? That's not really the important part of the example, even though it's handy to leave it as exact. This is how much. So when this sphere has radius 3, every time I add on another centimeter of radius, I add on 113 centimeters cubed of volume. That's wild. But think about a sphere that was all around. It would take a lot of cubes around the outside to add on to the volume. One little bit of radius adds a lot of stuff around the outside. All right. Let's do an easier one. That was a geometry problem. We'll switch over to a biology close to a chemistry type problem and see where the derivative pops itself up in biology or chemistry. The number of bacteria is given in a culture by B at T equals 10 to the power 6 plus 10 to the power 5T minus 10 squared T squared. You science people hopefully are getting used to this. That number of bacteria it's not going to be 7 bacteria. Bacteria don't travel in 7s usually. There's a lot of bacteria. And so there's some scientific notation thrown in here. I'll go back and forth with the scientific notation so you science people can see what's happening. At the same time, I don't want to blow away people who aren't in science classes. It says the number of bacteria in a culture is given by B at T hours. Find the growth rate. Oh, there we go. Another flag word for us that in advanced functions would have been 2 to 2.1, 2 to 2.01. Last chapter would have been limit as h approaches 0, f at x plus h minus f at x over h. That's how we would have found instantaneous rate of change. Now this is, as soon as we see that, we're thinking, take the derivative, find the rate of change. That's what b prime does. It's the slope of the tangent. It's the instantaneous rate of change. It's all of those things. So b prime at t here, we'll just do this carefully because the only real concern, this is not a particularly hard derivative, the only real concern is these crazy derivatives. 10 to the power 6, what's the derivative of 10 to the power 6? 0. That's just a number. I know it's a really big number, but its derivative is still 0. Then 10 to the power 5t, same as what I was talking about up at the top there. I can just cover up the 10 to the power 5, go, the derivative of t is 1. And so the derivative of 10 to the power 5t is 10 to the 5. And I'll write the 1 there, but you might be at the point where the 1 actually confuses you, where you're like, it's just 10 to the power 5. If that's confusing at all, let me quickly do a couple derivatives over here. What's the derivative of 10t? 10. What's the derivative of 1,375t? 1,375. What's the derivative of 10 to the power 5t? 10 to the power 5. And the 1, again, may or may not help you. And then this last one, bring down the 2 and reduce the power by 1. I'll put a 1 there, but most of you have probably progressed past where you need to put a 1 there. Can I tidy this up at all? I think I can. B prime at t equals 10 to the power 5 minus 200t. I don't know what your science teachers are telling you about scientific notation. If it's just exponent 2, do we really need the scientific notation? And the answer is yes. Sometimes. It depends on what you're doing. And other times it's like, well, isn't 200 a lot easier to look at here than this? So I don't answer those questions. I just talk about them. But they wanted B prime at 12. How much is the bacteria growing at 12 hours? So I got to sub a 12 in here. And so I get 10 to the power 5 minus 200 times 12. I'll get some help from my calculator. And then we'll talk just for a moment about scientific notation. Just for a moment. 10 power 5 minus 200 times 12. I get 97,600. And is there a science person out there who can help me put this back into scientific notation? I actually don't know the answer. I don't know where you're at with scientific notation in your classes right now. 9.76 times 10 to the power of, I didn't hear what you said. It's a little more than 2. 4, yeah. 1, 2, 3, 4. And if you haven't seen scientific notation before at all it is putting things one significant digit in front of the decimal and then use an exponent. It's really good for combining with other things that are scientific notation or comparing for other things. This is fine in calculus class, 97,600, but I just mentioned that for the science people, okay? What's the units here? Bacteria per hour would be the unit here. Bacteria is like that. It grows fast. This is why you can hang out with a friend on Monday night who's coughing, and by Tuesday afternoon you're already like, whoops, I think I picked up what they had there. It doesn't take long for you to feel the effects of somebody else being sick. Any questions there? So we did no physics today. It's good. Finally, some non-physics example for you non-physics people. We did geometry. We did biology, chemistry type stuff. And for you economics people, some economics examples. Whoo, finally. But first, a story, which I may have told you before, but I really love the story, so you're stuck with it. Here it comes. Both of my daughters did this once. True story. Both Bella and Chloe, at somewhere along the way, noticed there was a garage sale in the little village we live in, and they were convinced that they were going to make a lemonade stand. Did anyone ever make a lemonade stand? Yeah. Kids love this. They were wound up. So I'll use Chloe as the example because she's the younger one. This was just recently. And it's mostly a true story, actually. That's what's great about the story. It's mostly true. A couple little modifications for what I have to teach today. So Chloe comes to me and said, Dad, there's a garage sale this weekend. I'm like, yeah, I know. I knew what was coming. I knew what was coming. She says, can I make a lemonade stand? I'm like, sure, we'll make a lemonade stand. So off we go to the store. We buy one of those big fancy jugs. Yeah? We buy some lemonade mix, bag of ice. Off we head home. She makes lemonade, mixes it up, and I think the bill at Sobeys for all this stuff was $23 or something like that. Yeah? She goes out, sells lemonade all day, wearing her ponytails, which that's the number one thing in a lemonade stand. Get your ponytails on, you'll sell a lot of lemonade. Had her ponytails, sold a lot of lemonade, comes in and said, Dad, I made $80 selling lemonade. And I was like, I don't know if you made 80. She goes, no, I did. I got 80 right here. And I'm like, yeah, No, you didn't. What did Chloe forget? The cost of supplies, which was $23. I know what you're thinking at this point in the story. You're like, you giant jerk. Did you make her pay the $23 for the stuff from the store? No, of course I didn't. But that's not the point of the story, right? The point of the story is, in economics, in business, you've got to think about these things. It's fine to make $80. That is, right now, I could make a lot of money on iPhones. I could bring a lot of money in. If I sold them for $200 each, I would sell a lot of iPhones. I would bring a lot of money in. But that would forget something, that it's going to cost me $500 or $800 or $1,000 per iPhone. I'm going to go out of business really fast. It's going to be a lot of revenue, though. There's going to be a lot of money coming in, but it's not going to pay the bills. This is the essential question in economics. Will I bring in more money than I have to send out? Okay? So, revenue. Simply put, this isn't a good enough definition for you economics people. If you're going into economics, you have to do a little bit better. But this is money brought in. This will be good enough for us. Money brought in. And Chloe brought in $80 at her lemonade stand. Cost is money sent out. And again, for you economics, accounting people, you'll label these costs all sorts of different things. There's fixed costs, there's variable costs, there's operating costs. There's lots of different costs out there, and we won't get too carried away with all those things. We'll just do a little math to get you ready for those fields. Yeah? Profit, simply put, Chloe did not make $80. She made 80 minus 23. She should have taken her revenue and subtracted her cost. Economics, business people will argue that's the most important equation in the history of humanity. They're completely wrong, but it's the world they live in. They got to know, how much profit did I make, revenue minus cost. Average cost. I'll just write cost per item. That's a pretty good starting definition of average cost. It says, how much do I pay for each item that I made? The best example I can think of for this is business cards. If you go to order 1,000 business cards, it might be like $100. But if you order 2,000 business cards, it might be $110. Once they've got the design on, once they got it all set up, making you more business cards is really easy. There's a lot of initial cost there. And so we're very interested in average cost. How much per item? And marginal, again, I'll keep the definition simple. This is the word that business people use for rate of change. And if you're in those courses, you'll see there's a little more to it than that, but that's where we'll start with it. When you see the word marginal in a question, they mean rate of change, and for us, we mean derivative. Calculus people, when they see marginal, they immediately think, oh, we're going to take the derivative there. Yeah. So some definitions for you for this part of it. But I hope revenue, cost, and profit are ones that now that I've taught it once, you're like, I don't really have to memorize those. And I'll show you average cost before we're done. Here's my only example for this. Chloe is running a lemonade stand. And I calculated all the equations for her. She calculates her revenue function as R at X equals 20 plus 2.50X. She thinks the money she's going to bring in $20 at the start and then $2.50 for each glass of lemonade. Why did she get 20 at the start? Well, I was really scared when the morning started that she wasn't going to sell much lemonade, so I just slid a 20 into the box before we started. So she started off with 20 bucks. Or better yet, Grandpa came out and paid $20 for the first glass of lemonade because he's a good guy, right? So she's going to make 20 plus $2.50 for each glass of lemonade she sells. Her cost function is really complicated. C at X equals negative 0.01X squared plus X. Where does this come from? Well, there's a lot going on with cost. She bought her. This isn't accurate, by the way. I'm just trying to make it sound sort of accurate. She had to buy her jug, and she's going to have to buy ice every so often, but not very often. She might have to buy some more lemonade. We might have to rush back to Zoe's and get her another can. So this is a very weird cost function, but this is how much she's going to have to pay out. Where X is the number of glasses of lemonade. Calculate the profit function. So you'd write profit equals revenue minus cost, or you might write P at X equals R at X minus C at X. That's clearly a much better calculus statement, the second one. So my P at X here is the revenue, 20 plus 250X. Subtract the cost function, which is 0.01X squared, plus X. So her profit function, let me just tidy this up a little bit, 20 plus 1.5X minus 0.01X squared. Let me just double check that to make sure I didn't make a mistake there. 20 is the revenue. 250X minus an X is 150X. And then minus, oh no, it was minus here, wasn't it? I knew that didn't feel right. There we go. It was a minus in the brackets for the cost function, and when I subtracted that, I got a positive. Let me just segment that off so I don't get it confused with the next question. Any questions on profit functions? Now, if I want to know the profit, if she sells 40 glasses, I just sub in 40. If I want to know the profit at 20 glasses, I just sub in 20. If she wants to know when she's going to make $100 for a new Lego set, I put 100 over here and solve the equation. See, I can do all sorts of things with that equation once I have it. Calculate the cost at 20 glasses of lemonade. So our cost function for 20 is negative 0.01 times 20 squared plus 20. We'll punch that in. So if she makes 20 glasses of lemonade, how much money has she spent? $16. It only costs her $16 to make 20 glasses of lemonade. So let's calculate our average cost. And I'm going to use a equation in a second, but I'm also going to write it down there. Question? Is good? Okay, good. I'm just going to use my brain the first time, okay? I'm going to do this two different ways. Oh, two different ways, C and D. In C, I'm just going to think about this and go, so if it was $16 that it cost her to make 20 glasses of lemonade. How much for each glass of lemonade? This will help her decide what she should be selling these for. Well, it's just 16 divided by 20. Take the 16 bucks and divide it by the 20 glasses of lemonade, and I get $0.80 per glass. That's her cost. That's really important in business to go, how much did I actually spend per glass here? She's only got 80 cents in each glass, so as long as she sells them for more than $1, she's home free. We already know she's from here that she's selling them for $2.50 a glass. But the 80 cents tells her where she's at, what she's got to do to make sure she makes money. But the average cost function looks a little different. So let's rewind a minute. Now pretend you did your homework and you did average cost here, and someone said, where did you get 16 divided by 20? What would you tell them you're doing in words? Without using the 16 and the 20, what do you got to do to these? What two numbers do you got to get to be able to find average cost?
X is the number of lemonade glasses, and you put the cost function on top and you divide it.
Yeah. The numerator is the cost. How much did this cost? In her case, $16. But in our case, for a function, it's negative 0.01 x squared plus x. But then you have to divide by how many glasses of lemonade, and that's just x. We can do a little better in this case. We could tidy this up a little bit. It won't always be true that you can tidy it up nicely, but this one does. Why does the average cost drop on this? Why would the average cost be going down? Well, it has to do with the initial price of that. Oh, go on. Yeah.
Economies of scale.
What's that?
Because her cost function is structured the way it is, then economies of scale starts to come in. So she is able to produce more, and her cost will go down.
Yeah. The cost of the jug was a lot. Imagine if she only sold one glass of lemonade. She'd have to sell for 25 bucks to make up the cost. But as that cost of the jug spreads out over a lot of glasses of lemonade, it becomes less and less. So the average cost keeps dropping because she can spread that cost out. This is why when you build a new building or you build a new factory, you want to use it for a long time because that cost gets spread over a long time. And then marginal cost. If cost was negative 0.01 x squared plus x, then marginal cost is just c prime equal to negative 0.02 x plus 1. So marginal, well, there's a little more to it than that. There's a little more to the marginal word than that. But for our purposes, marginal will just mean take the derivative. Find the rate of change of cost. And the rate of change of cost here is negative 0.02x plus 1. Notice the domain. This only applies from 0 to 50 glasses, which actually fits into my lemonade thinking. This only applies for the first 50 glasses because after that she's going to run out of ice, she's going to run out of lemonade mix, and then she's going to have to start again. So it's only from 0 to 50 that the domain really fits here because apparently 50 glasses is the most you can make with the mix she bought. Are there any questions about that?